Okay, so I suppose I'll start. So I welcome the viewers to this problem solving and live interaction session for the subject engineer experimental stress analysis. So we'll be discussing the contents of week 2 of the course. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics at IIT Madras. I'm working under the guidance of Professor K. Ramesh and Professor U. Saranam from the Civil Engineering Department. So let us get started. Let us look at the first question. The gauge length of a strain gauge is shown. Gauge length of the strain gauge shown in the figure is the distance from the points A to D, B to C, C to D, or B to D is what is asked. So essentially, we just have to identify the gauge length for the strain gauge. So before that, I'll just quickly show how a strain gauge is basically constructed. Now, if we see there is a soldering tab like that. Like that towards the end there is a bulbous region where we generally solder it, and then we'll have the same at the other end as well, like that. And in between these, essentially we will be having a thicker region, a bulbous thicker region, and then we have again the wires going, and then another bulbous thickest region, and then the wires coming back. So this thing is repeated like that, and it is connected. So why this is done? Essentially, as we will see in the next subsequent weeks also, that strain gauge basically works on the principle of change of resistance brought about when a wire is stretched, when a conductor is stretched. So now if we want to measure strain at a point, naturally we cannot accommodate a longer conductor. But for us to have amplified signal, we do need a long conductor. So one way to circumvent this problem is that we basically coil up the conductor like that to a length that is as small as possible, and we provide bulbous ends so that the transverse effect don't affect much. So essentially, if we have a wire and then I stretch it, uh, let us say that I have a wire and I stretch it. Now its length will increase, its cross-sectional area would decrease. So essentially this would lead to a change in the resistance. Now because I have coiled it up, what would happen is that length along, so here the main direction of loading is that. So these wires, these vertical wires, they get stretched like that. At the same time, there will be some Poisson's effect coming in, because of which there will be a strain in the transverse direction. So we don't want that transverse strain to affect the length of these portions, because that will lead to an error accumulating over my result. So what we do, we basically increase, make it bulbous, make it thick. Essentially what we are doing is we are making area much greater. So that will lead to those effects dying down. So essentially the results that we'll get will be dominant with the response along this direction. Will be dominant with the results along this direction, or the direction in which we want to measure, the direction in which our gauge length is. So with that preamble, if we revisit this, we can see that this is nothing but the bulb where we will solder the tabs and connect it to our strain gauge amplifier in order to read the strain. And then the wires go like that. So essentially what I'm saying is, if I superimpose this in some sense over that, and then I stretch it in some way, so I will get my wires like that. in here. So those wires are what form the gauge length. So essentially my strain is being measured with that as the gauge length. So from here we can see clearly that that distance is represented by the distance between point B and D. So essentially my strain gauge is having a gauge length between the points B and D. Okay, so anyway, I had started at 6. So this is the first question where we have a strain gauge, and I just went through how a strain gauge is constructed. Basically, we have a two soldering tabs, and then we have the wire coiled up like that, and we make the ends bulbous because we don't want the transverse Poisson's effect to creep into our calculations. But more on this construction of the strain gauge will be dealt with in detail in the later course, in the later part of the course. But essentially, what we are trying to measure is this is our conductor whose length is changing, and that is the change in that length over its length is what we are trying to measure as strain, which is why the distance between the end of the soldering tab and the end of the other end of the strain gauge what represents the gauge length of the strain gauge. Are there any questions? Okay, okay. Okay, so I'll move on to the next question. The resistance of a wire conductor changes with which of the following is what is asked. Uh, Whether it is applied stress, whether it is temperature, whether it is both A and B, or none of the above. So for the resistance we have studied in physics for any material, let me take this as a wire. Let me just put it like that. Let me call this cross section A and this length as L. And let this material, let the wire be made of some material M. So the resistance of this wire is given as the resistivity of that material M into length by the area of cross section. So essentially what happens when we apply stress to any material, there is change in the length, and due to Poisson's effect there is change in the cross-sectional area also. Since it is a wire, it doesn't have any transverse stiffness, so we will not talk about bending or twisting it. We will essentially treat it as a truss member. There will be only uniaxial stress that is applied. So the length would change, the area would change. So definitely applied stress causes a change in the resistance. Similarly, we know that for a material, when there is a temperature change, also there could be change in length, change in the area. But in addition to that, there will be change in the resistivity of that conductor. We know that some certain materials, if we cool them, their resistance reduces. So that is the principle behind superconductors. So in such case also, change in the temperature affects the change in the resistance. So essentially what we have here is both A and B change the resistance of a wire conductor. Now why this is important? As we saw here, if you are to take this strain gauge, if I have to take this strain gauge and construct it using some wire, essentially, and if I paste it over a specimen, now what I ideally want to measure is the strain due to the mechanical load that I've applied to that specimen. However, due to temperature effects also, there will be some strain that will creep into my calculations. So I should be in a position to eliminate that so that I obtain the response only for the mechanical stress that I'm trying to measure, mechanical strain that I have induced. Because temperature stresses could be significant as well. And if that be the case, then that will throw off my results and my experiment will not be accurate. Which is why we need to know this background that resistance of a conductor is affected by that, and a conductor is what we are using to construct a strain gauge. So we need to look for ways and means to eliminate temperature stresses, eliminate the temperature effects creeping into our calculations. How we do that is a part of a part that will be discussed in later weeks by specific arrangements of the Wheatstone bridge. But essentially, that is the essence behind asking this question. Okay, so let me move on to the next question. And midway, should there be any doubts, please feel free to stop and ask. Grids are marked on a mechanical billet before and after deformation. Grids marked on a mechanical billet before and after deformation are shown. What kind of information can be directly obtained from this? Now, what we are essentially saying is there is a indenter like that and one like this, and then as it is loaded into it, we are able to see that such patterns emerge. A grid that was marked. So we can see that these grid lines were basically scribed onto that metal. And these have now become like that. So for a metal to deform visibly, it must be an enormous amount of strain that it has undergone. And we are readily able to see that deformation with our eyes. That a material point that was here has been mapped to some place. A material point in the grid in that same square has been mapped to some other place. So like that we have mapped. So essentially what it is trying to give us is the displacement in that plane, in the plane in which we are viewing the screen. One material point got mapped to this point. This got mapped to here. So what it is giving us is the in-plane displacement information, which is readily available directly. Now, if we were to calculate these displacements with very fine grids, let us say, and if we are able to get the plot of the slope of that displacement, then we will be able to measure strains as well. And so same goes for curvature. If we are able to get the change of slope of the slope itself, that is the double derivative of the displacement, then we will be able to get curvature information also. And since we are talking in plane, so it is not out of plane displacement information that we are seeing. We are essentially looking at in plane displacement information. Okay, so I hope that that is clear. But essentially what we need to keep in mind is that this is visible displacement we are seeing from our eyes, which implies that this is definitely well beyond the elastic zone, and we have already reached a plastic condition in metals. Okay, so let us look at this question. The fringe pattern shown in the figure is which of the following? Observed under white light for a beam under pure bending. Observed under white light for a beam. So one thing that is common among these points is that it is observed with a white light. Now, why that is important? As we will see in the next session or so, when we get into photoelasticity, that this basically these fringe patterns are from photoelasticity, and these represent the contours called isochromatics. Why is it called isochromatics? Iso means same, isotherm, isobar. So iso generally represents the locus of all the points that are indicating the same parameter. And chromatics, chroma means color. This word chroma means color. So we are able to see that whichever points have the same color, the the entire line here, for example, has black color. Similarly, the uh, entire row of pixels, so to speak, have the pink color. So essentially, these are by its very nature connecting and giving contours of constant color. That is why these are called isochromatics, and these carry the information of sigma 1 minus sigma 2 equal to some constant k. What that k is, that we will see as we discussed in the previous session also. So when we use white light, we basically get colored fringes. So that ends this part of the question, that all are observed in white light. So that's fine. Now we come to the mechanics part of it, whether it is the fringes seen for a beam under pure bending, under 3-point bending, under uniaxial compression or uniaxial tension. So let us try to reason out what it could be based on what we know about our isochromatics. Sigma 1 minus sigma 2 equal to k. So let's see that. Now let us say that I took a beam. Let us get some things out of the way. So here, let us say that this is my x direction. Good evening. Have low battery and mobile and no alternate computer. I will. No problem. Thank you for informing. Anyway, you could. I don't mind all that. So you please suit your convenience and watch this. So if there are any constraints because of which you are not able to attend or leave midway, yeah, I'm doesn't I don't have a problem with that. So you please suit your convenience. Thanks. Okay, so let us say that we define this as the x direction and this as the y direction. And first, let us apply it with a uniaxial tension of sigma. Some sigma I have applied, sigma being some variable. Now for this case, let me take a material point over here and let me zoom it. Now I know that I am talking only the in-plane response, that is x and y plane only we are talking. We are not talking presently about the out-of-plane response. So in this case, I know that I can draw the state of stress in this element. In this element, at this point, I have the stress element like this. Or let me go one step deeper. Let me not take this directly. What I do is, I'll take this and let me pass an imaginary section like that. Let me pass this imaginary section, and what I'll do, I'll just cut this. Now I know when there is something in uniaxial tension, if I apply equal forces on both the ends, it deforms, but it is still in equilibrium. So there has to be an equal and opposite force that is getting applied. So that force, uh, actually, while I have represented that as sigma, let me correct it a little bit technically by specifying that as some force P. Because essentially I will be applying a force. I'll hold a point and I'll pull it. So I've applied that force P. Now this has to be balanced by mobilization of some stress. And I know since it is in uniaxial tension, when I'm sufficiently far away from the loading points, something, the stress that gets mobilized, sigma, is nothing but P by A, where A is my area of cross section of that member. When out of plane thickness is not covered, it is just the depth of the member. So far so good. This much we know. I know that this is the state of stress at all the points in this along this cut. So if I were to take one point now and then I zoom it in here and let me draw the state of stress at that point. Now here state of stress I have, this is sigma, this is again sigma. I know it is being pulled, it is under tension. Is there any sigma y? There is no sigma y. Similarly, I'm just pulling it, so there is no shear as well. So this happens to be the complete state of stress at that point. Just uniaxial tension. Now, in the absence of shear, I know something that in the absence of shear, on a plane where shear is absent, whatever normal stress is applied or induced is my principal stress. So in this case, what is my sigma 1? My sigma 1 is sigma itself. And what is my sigma 2? Is nothing but 0. So these are the two principal stresses in such a case. Now from here, what can I imply? That sigma 1 minus sigma 2 is nothing but, it is just sigma, which is nothing but P by A. So for a prismatic member where A is constant, I have applied a force P at the ends, and I find that at every point. Now this section which I've taken here, I may as well take it here, here or here, anywhere along the length of that member, but far away from the loading points, let us say, which is where we are actually looking at. In such a case, because this section, it has not said that it is covering the loading point. So I am assuming that it is a section of the member. So in such a case, no matter where I take, I get only one value of sigma 1 minus sigma 2, which is equal to F by A, which happens to be a constant. So what does that imply? At every point, if sigma 1 minus sigma 2 is equal to constant, from my concept of isochromatics, I should be able to see only a single color throughout. So essentially, it will be only black or only pink or only blue or something like that. But here we are able to see a variation in the colors across this distance. While there is no variation in this direction, there is a variation in this direction. So we'll see why that is. So essentially what that implies is it cannot be uniaxial tension from inference. We can deduce that it is not uniaxial tension. If the same case I were to consider, but just reverse the force. Yes, sir. Please go ahead. Yeah, along the direction of the load. This is essentially It is like I have taken a section here. Yeah, yeah, yeah. So whatever we are seeing is in the plane of the screen. Uh, Even the sections consider and what is represented. So now if I were to take the same case and I just flip the load, make it minus P, what do I think, what do we think that will happen? Just it will get reversed. Similarly, this will become a compressive stress. That is the only difference. So what would happen? My state of stress will change. This will become compressive. That is all. In such a case, okay, instead, why don't I draw it? In fact, if this is the case, now what I have done, I have just flipped it. So let this be A, and I apply it with a force P. So this gets reversed, and so does this. So this gets reversed, and I have my state of stress here as I have compression equal to sigma, nothing else. So sigma 1 in this case it is 0. Sigma 2 is nothing but minus sigma, because we follow the convention that sigma 1 is greater than sigma 2 greater than sigma 3. When we talk about just two dimensions, we may as well concentrate on the first two, but it is always arranged in the algebraic order. So in such a case, sigma 1 is 0, sigma 2 is minus sigma. So therefore, from here, sigma 1 minus sigma 2 is again coming out to be sigma, which is P by A, again a constant. So what do I infer from this? That not only will I not see any change if I were to flip the force, in fact, the value of constant principal stress difference is, in fact, the value of the principal stress difference is the same at all the points. This tells us something interesting. So if I take a photoelastic material and if I pull it with one force P, then I do one experiment and then I reverse the direction of the force and I compress it with that P. From what we understood, it is telling us that there will be no change in the color. We will essentially be seeing the same color. So photoelastic fringes cannot differentiate between tension and compression, tensile stress and compressive stress. That is because sigma 1 and sigma 2 remains the same. So this is something interesting now we see. Now this implies that our uniaxial compression is also not the case. But we have got one information from here is that whether it is tension or compression, it will give us the same color. Now here, if we look at this thing closely, I could derive it from first principles using the equations of pure bending and equations of 3-point bending, but I am going by inference here. What we see about this line, if we see this line, let me color it with some other color. If I see this line, I'm able to see that the fringes are nearly symmetrical. That is, it goes from white to blue to yellow to blue again, green and pink. Here white, blue, green, pink, again little bit of blue, then green and then pink. So it seems to be symmetrical about this. So one possibility is that there is tension on one side and there is compression on one side, and it is not able to tell the difference, which actually is the case. Now, if we see the distance between these 2 points, the distance between these 2 points is nearly the same as the distance between these two. This distance is same as this distance because these fringes are essentially equidistant. So that tells us that there is a linear variation in whatever parameter we are saying. So when will there be a linear variation? When the thing is under pure bending. Because we see from our flexure formula, it gives us m by I is from flexure formula which is derived for a case of pure bending. What do we know? Bending moment by I z is minus sigma x by y equal to E by R or rho, howsoever you represent the radius of curvature. So if I were to just consider this, this tells me that sigma x is nothing but minus mb by Iz into y, which again gives me that sigma x is directly proportional to y. It's a linear variation of y. So as y increases, sigma x increases. And for the case of pure bending, there is no sigma y or tau xy. In which case, for pure bending, sigma 1 is sigma x when we are this will actually hold in one case where this comes out to be positive. That is, when the bending is when the bending moment is applied, whenever the axial stress sigma x is positive, it will be sigma 1. Whenever it is negative, it will become sigma 2 because of the algebraic order. And sigma 2 is equal to 0. Let us say that our moment is applied this way. Let us consider that our moment is applied this way, mv. So for this case, if my moment is applied this way, if this is my origin and this is y, when I go y positive, then I should get a compressive stress. So when y is positive, I get a compressive stress. So this will be, I can mark out the domain also. When y is greater than 0, sigma 1 is 0, sigma 2 is minus sigma x. When y is less than 0, sigma 1 is sigma x and sigma 2 is 0. So from here, sigma 1 minus sigma 2 is invariably sigma x, which is nothing but we just now saw what it is. It is mb by Iz into y. Which is a linear variation, which is why we are getting such fringes. And one more thing to note here is, we know for the case of pure bending, whichever is the axis of symmetry is the centroid of that cross section, and that happens to have no stress. So from here, we are able to deduce certain things, that whenever we see a black fringe for this material, black color, that implies that the sigma x is 0. And since sigma y is also 0, it implies sigma 1 minus sigma 2 equal to 0. So that is what this central fringe implies, the neutral axis fringe. And then as we go this way, we see one particular variation. Same variation is observed on the way down as well. Again, there is some more information that is embedded here. We can take it up in a later session. Anyway, so yeah, are there any questions based on what we discussed now? Is it clear? If there are any questions, you please feel free to ask, because I might be explaining with one particular direction in mind, but ultimately for this session to be fruitful, I suppose if there are any doubts, if I take them, I think I'll be. Yes, sir. Please go ahead. These these fringe patterns will be visible. Ah, okay. Uh, no, let us see what the fringe pattern actually comes with. It is fringe pattern is getting found because of this, right? So our IZ, let us say that our beam is constant cross section, and it is prismatic rectangular, or any section for that matter. So throughout the problem, as we are increasing the load, IZ is essentially the same. The bending moment, as we increase the load, the bending moment also increases. And Y is just a plotting parameter. So what we will see at each and every section, when sigma 1 minus sigma 2 has reached some value here, this color appears. Now if I load more, whatever the stress was here will get percolated here. So what I will see is that the fringes become more and more dense. So the particular photograph that is shown, that is for one particular bending moment. If I increase the bending moment or decrease the bending moment, although the pattern might still be linear, equidistant, but the fringe density would be different. Is it clear, sir? Okay. In case I have not completely answered you, please feel free to discuss and ask back, because ultimately the idea is that your doubt should get resolved. So in case I'm not able to completely convince you, then you please get back and I'll try to articulate it in a different way. Is it clear, sir? Okay, okay. Yeah, yeah. Those such live experiments are shown in the actually in the lectures. So as we increase the load, what will happen? So one of the examples also deals with it. So we will see as we go along. Okay, so fine. So now we have this question. Different regions of stress strain curve. So we have a stress strain curve that is linear like that. Let me zoom in and draw it first. So I have a stress strain curve that is almost linearly elastic. And then there is a kink. And then there is some strain hardening taking place. And ultimately it fractures. So this is my stress strain curve for mild steel. Fine. That is shown along with some regions indicated. So we have one region that goes like that. That is region A. This is region A. And then we have B, B, which is like this. And then C is somewhat here, somewhere over here. And my pink color is like that. So one region is over here. I'm just to demarcate it, I have drawn it like that. So please don't get confused with this. What are we trying to ask in this question is what is the range of strain or stress up to which this can be applied? So we have four regions which are marked with the letter A, B, C, D. As an experimentalist, identify the region where the technique of photoelasticity can be employed. So essentially, photoelasticity works under the linear elastic range. So because in the name itself it says photoelasticity. So when we go beyond the plastic limit or yield, then we are looking at another method called photoplasticity. So essentially photoelasticity deals with areas in the linear elastic range. So here we are able to see this is the elastic limit or the yield nearby, so to speak. So from here, right from zero, because we saw that when the stress is zero, I'll see a black color. So right from the moment I begin to load it, I'll see the evolution of fringes till the material has attained yield. It is not that after that I will not see fringes. It is just that after that I will not be able to interpret it using the theory of photoelasticity. So I might have to uh, use other techniques at my disposal. So this starts as a load as we begin to load the model till it reaches its yield. We have its validity. So essentially, photoelasticity is this is photoelasticity. If you look through in the lectures, it is described what each and every of these what each of these reasons basically represent. So I'll just go briefly through that. Essentially, this area doesn't start from zero. It has some threshold strain. This is strain. So there is some threshold strain from which it starts and somewhat goes beyond the plastic limit. So this is where we can use brittle coatings, because if we coat a material with uh, a brittle coating, and we load it, it is not that as soon as we start loading it, the coating will fail. So that coating also has some strength, and it has to cross one particular strain for it to develop those cracks so that it can be interpreted. So this is that threshold strain beyond which brittle coatings can actually it'll start showing the cracks. So that is why this is brittle coating. This is brittle coatings, and then another method, if we take a specimen and then we put a strain gauge over that. So right from the moment we start the load, like photoelasticity, that will also show a strain response. That will also show a response. But unlike photoelasticity, which will give you fringe contours of isochromatics, strain gauge amplifiers will give you the value of strain. So that also very much starts from zero, right from the start of the experiment. And it can go well beyond the uh, plastic region. It is quite versatile that way. So there is a limit up to which it can go is because even the wires that you are using, that should not yield because that is also getting loaded. So that should not yield. So there is a limit to that. So strain gauge, of course, this limit should not be exactly read. These are just to give an idea of as to which range it is applicable in, so that we know when we are looking at some problem in hand and we anticipate that there is a particular level of stress or strain that we are testing this for. If it is in the very low stress region, then what are the methods that we can apply? For example, if it is very much below 300 microstrain, it is just a lab experiment we are doing. then even if we coat it with brittle coatings, we will see that no cracks will get formed. So in such a case, brittle coatings is not applicable for that level of strain or level of stress or strain that is getting induced. So this is to check the suitability of the method based on different criteria. This one criteria is what is the level of strain that you anticipate it to come. So this is essentially the validity of our strain gauges. And then again, as it is said in the lecture also, we have this technique called thermoelastic stress analysis. So that gives whole field information, and this entire, it has a wide range of applicability, but it is equally complex and equally expensive to set up. So many of these might look just like matters of fact that we are stating. The idea is sometimes knowing this also can help. So time and again, when we repeat these things, it will give some ideas of there will be some percolation and retention as to what goes about in each method. And then, of course, number of references and papers have been given in the lecture for interested people to learn more. Because even these techniques, we even within these techniques, you will find that one technique there will be a number of books, detailed full volumes, which deal with the different variations of that method. So to condense everything into a semester's course is it is just not possible, which is why the course is offered with the to give an overall perspective of the methods, their merits, their demerits, where they find their applicability, where they are generally being used currently. And then we'll go deeper into a couple of them, namely photoelasticity and strain gauges that we will threadbare see along with brittle coatings and photoelastic coatings. So these things we will see in much more detail. But other than that, you might find that there are certain things that have been left which have been introduced, but not we have not got deep into that because it is because of this constraint that it has to be confined within one semester. And so, other than that, there are many references that are given in the lecture. So, if you do want to explore more of that, you are free to refer them. So, this is that thermoelastic stress analysis TSA. Anyway, as for this question, it is asked that as an experimentalist, identify where the technique of photoelasticity can be employed. This we have identified as D, which starts from zero stress to the elastic limit. Okay, so let us go to this question. Answer true or false for the following statement. Type T for true, F for false without any spacing. So if we find everything is true, then we'll just write four T's and so on. This is because it is not possible to always have manual grading, so we have to shift to computerized grading. There are certain merits and demerits associated with that. So for it to interpret that objectively, we need certain conventions, which is why such things have been given. Okay, that has also given. If the first statement is true and the others are false, you type it like that. Anyway, so let us look at the points that are given. Brittle coating technique is the right choice to identify the zone of interest for a refined analysis when it comes to analysis of large components. So if we have a large component, what will govern our design? Essentially, design of anything is based on certain criteria. One could be a stiffness criteria, or it is also called serviceability. Where you have to limit the deformations that come in. One is the strength criteria, which is also called the ultimate limit state criteria, where you have to confine the maximum stresses that come in to a safe threshold. So in such a case, If there are large components and if we have to design something for strength, naturally we will have to identify which is the portion that is getting stressed, the stressed to the hilt, to the maximum level, so that we provide adequate material and reinforcement at that point, so that the design is safe for that purpose. So in a very large complex structure, in order for us to identify those zones, brittle coating happens to be a very good technique. Why? Because when we coat the material, as we saw, up to a certain threshold of strain, the brittle coating show no cracks, so it will just be a uniform coat that is applied over the large component. And as soon as we load more, there will be cracks appearing at certain locations. So the locations at which the first cracks appear, those are the peak stressed regions. So at once, it gives us a way to identify which are the areas where the stresses peak. Now, what we do, we go into that area, and then we can use other techniques such as strain gauges in order to correctly identify what those levels of strains or stresses are, what are the levels of those stresses and strains induced, and whether they are within the permissible thresholds. So that way, brittle coating is very ideal in identifying quickly which are the places of large stress or strain, so to speak. So this is true. This is true that it is so. When one wants to get whole field appreciation of a stress field, then strain gauge is the right choice. Okay, why this is not so? Because let us say that again we have that large component. Now, if we have to paste a strain gauge, we understand that there is a strain gauge. Uh, it's a small measuring strip which we have to paste. Now, this begs the question: where would we paste it? Now, if we want whole field information, whole field meaning throughout the domain, we want the information. For example, if we go to this example again, I have a beam and this is giving me the information at each and every point, each and every pixel of that material point of that beam. So this is whole field information. I'm able to see what is happening uh, throughout the beam. Now, one may argue that what happens beyond this is not shown. That is not shown, but it is not that photoelasticity cannot show it. It is the makers of these questions that have not shown that. So it gives us whole field. All optical techniques are mostly whole field. So in such a case, if we have to go with the measurements by strain gauge, it is not possible because you cannot attach a strain gauge to every material particle. So whole field information you cannot get using a strain gauge because it's essentially a point by point technique. Nonetheless, strain gauge is very accurate. So what we do is we first refine our analysis so that we identify where to place the strain gauge. And that is what our first point talks about. Like we identify that using brittle coatings. And then once we have identified, now we know where to concentrate. There we can use strain gauges in order to make precise measurements. So this is not true. Photoelasticity can give quick comparisons for different designs. Why this is so? Because for one, the fringes are very sensitive. Secondly, it is whole field technique. So in the lecture also it is shown that if we have a spanner and if we have circular fillets like that, and in the other case this is smoothened out with a single transition curve. So in the lecture it is shown how the fringe patterns actually show a marked change in both of these. I hope you are able to understand what I'm saying. Here it's a circular curve and then here it's another circular curve. So there is no smooth transition. There are kinks over here. Whereas in this design, there are no kinks. It is just a uniform transition curve. In which case, we can see it is shown in the lecture how the fringe patterns will show the change. So these are very useful in comparing the designs. Essentially, what we want to see here is that none of the fringes ends at the ends at an angle or perpendicular uh, to the face. So we want it to be parallel so that there is smooth flow of the stress, which is why photoelasticity can definitely give a quick comparison. And I would suggest, if you have not seen this, you please do go to the lecture and see it once. It is very interesting how slight changes in the spanner shape uh, bring about market changes in the fringe features. D. Photoelasticity is not much useful for measurement of residual and assembly stresses. This is not true because photoelasticity happens to be the one of the very few techniques which can actually measure assembly stresses. Now, what are assembly stresses uh, or residual stresses? Essentially, if we have some component and we have mentioned that this is the torque that is to be set, if one of the uh, bolts are tightened more than that, it will lead to an imbalance, which will create an assembly stress, which will be out of the purview of your design. Because when you have designed that component, you have assumed that these four bolts carry so much load, and they have been tightened with this amount of torque or whatever. But that is an assumption you are making based on good workmanship. But if that doesn't translate into the final component because of some manufacturing processes and personnel, then whatever stress is getting induced into the component is not same as what you have idealized it to be. In which case there could be surprises that come about. So in very sensitive components, uh, what they do once the assembly is over, they also use photoelastic coatings to check the assembly stresses, whether they are uniform and whether there are any, if they are present and whether they are uniform. So if there are any anomalies or if the uh, stresses show what to say, they show asymmetry or things like that, then it will be a cause for concern. Yes, sir. Yes. Yeah. Yeah. Residual stress. Yes. 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 Actually, let us say that there is a component here. So there is something called a hole drilling method. What they do is, let us say that they are disjointed in some way. You paste a photoelastic coating here, and you take one record one measurement. Now what we do, we will weld this component to that. Of course, this has to be placed appropriately so that that doesn't melt away. But essentially, what we are trying to see is once this is fused with that, the residual stresses have already set in into this. Now, what we do, we will drill a hole into uh, this photoelastic sheet, and that will relieve those stresses. So the relief of those stresses can be seen as fringe pattern. So this is simply called the hole drilling method. There are techniques like that with which you can actually find out residual stresses. In fact, if you go to the website of micro measurements, Vishay micro measurements, there an entire setup of reflection polariscope along with this photo stress coatings and this hole drilling method, you will find the specifications. So those are essentially to find residual stresses that come about. And residual stresses need not come about just because of welding. Of course, you only mentioned it as an example, but it can be due to out of planeness, imperfections. There are many things that can come about. Even flange and webs, where they are connected, there could be residual stresses. So such at such locations, this method can be used. So I hope that is clear. Yeah. So this can be used for measurement of residual and assembly stresses. Yes. Okay. So let us look at this question. Answer true or false. Again, the same drill. Moire interferometry has found wide acceptance in electronic packaging industry to measure thermally induced stresses on tiny components. Interferometry in itself implies that it has high precision, and Moire interferometry is used in electronic packaging. So this might look like a statement of fact, but you can just check the lecture because there some additional background also will be given to you. And along with, as I said, along with some particular papers where you can refer more to them. So Moire interferometry is used in electronic packaging industry. Speckle and holographic methods are found to be suitable for analysis in MEMS application. Because these are very tiny and very precise measurements need to be made. Uh, Holography and speckle methods are quite accurate, so and very precise also, and they have a that is the measurement range is also you can take it down to very low scale and make measurements, which is why they are very much suitable. Holography is ideal for recording the mode shapes of a vibrating component. Now, holography is a method which measures the phase as well as intensity, which is why merging that output, you are able to generate a three-dimensional image as seen in the lecture. That is because not only the difference in the wave brought about by the curvature is measured, but its intensity is also measured. So you will actually have a realistic lighting effect that gets captured into this. So, since this is there, a vibrating component, it can easily measure its displacement vector where it goes, from which your mode shapes can be given one stimulus, your mode shape can be reconstructed. So holography is very much ideal for that, provided it is done carefully. Holography has it is very sensitive to vibrations that get introduced because there is a reference beam that you need to impinge on the specimen as well as the testing setup. So what we have to do, both have to be in sync. So there should not be any difference brought about in the reference beam that we sent. So what will happen is that the vibration control has to be extremely stringent. That vibration is different from this. What I mean to say is wherever you place it, the experimental setup should have extremely stringent vibration control. Only the test specimen should have the vibration, which will get effectively recorded. Speckle methods in its variation of stereography is used as an NDT tool in aerospace applications. Because aerospace application have lot of laminates and composites that are coming up, what happens is if there is any delamination between the two. For example, if we have assume a component has a cross section like that, and let us say that it is essentially some composite. So we have some bonding that has happened here. And our strength is derived based on the assumption that this bond will hold. Now, if it so happens that at some point this bonding has failed and there is a slight debonding that has come about in between these two, what will happen? This will become a place of, as a stress raiser, this will start acting because the stress is not uniformly distributed. So soon as this happens, it is only a matter of time that this expands. and then the complete thing fails. So such in such applications, this test of debonding is very, very essential. And this, how we can check that? Let us say if this was the case, and then we impinge some light here and some light here, and then I'm just giving a broad idea, and then we have a recording medium to which on a perfectly bonded area we record back the light. Now let us say that the light falls on this, it would get reflected like that because of that debonding. Similarly, a light impinging on this would get reflected. So when we record it uniformly, there will be some aberrations we will find at some locations because of this, uh, because of that effect in optical techniques. In such a case, we will be able to identify where such aberrations come and whether there is any debonding or not. I'm just giving you a broad bird's eye this thing of how it is done. Of course, the setup and everything is quite complex. But what we are essentially trying to see is that there is some curvature or some out of plane displacement that has come about, which is not uniform throughout the field. At some position, it has come. So if it is not accounted for in our design, then we may have to discard the component or take some corrective measures. Yes, sir. Yeah. Yes, yes. See, in ultrasonic, this thing you again have interference only. You are shooting out a beam, and then you are trying to record back what you are getting and trying to build something. This is an optical technique, so only the wave is differing. I hope you understand. Yeah, 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 yeah. So only the wave is differing. So it is very much similar to that only. Because we want to visually see it, so we are trying to do this. So in fact, all of them happen to be, yeah, thank you. So all of them happen to be true. Now, yeah, okay, no, not a problem. Yeah, please carry on. Not a problem. So we have these options, true, fine. Okay, so we have three plates with defects subject to tension. Same load for all the three cases, which can be viewed under the polariscope arrangement. That is, this is a photoelastic fringe pattern for these three plates. Essentially, we have some plates like this. So this was our first, let us say this was our plate. So first we applied it to some stress, tension. Let us say this is sigma. Now, as we saw in our earlier discussion with the beam, that once we apply this stress or the load in uniaxial tension, what is it that we anticipate? That the entire field should be having a common color. Now we can see that here in this case, we are having some shade of yellow and then it becomes somewhere it is black and so on. So it is varying. Ideally, it should have been a uniform color throughout. Now what happened is once we took this sheet, it had some defect. So this was the ideal case, which did not happen. The next case we saw is case A, where there is a hole here. In the next case, that hole got replaced with an ellipse like that. So with an ellipse like that. And in the limiting case, what happened is, so this was case B. And in the limiting case, let us say that we take the same load case, but instead of that, this thing, it was like this. let us say, on the edge, on one of the edges. So now to further worsen this, what happened is this ellipse got more and more eccentric. Now when the ellipse totally collapses in the limiting condition, there is nothing over here. There is nothing over here. So what is happening in the limiting condition? It gets converted to essentially a crack. Essentially just a crack because the ellipse has slowly degenerated into a crack. And so when we were trying to measure this, it was uniform color. But as these defects come about, we saw for the same load that was applied, we saw different types of fringe patterns coming about. And it has been given that it is the same load. So how do we interpret this is what is asked. This is A, B, and C. Now for this, we can see that there is black here. Some region is black. Now we can take the help of the same question here as we saw. Let me take it there. And we'll try to interpret certain things. Clearly the colors are not the same, but let me take it like that. And since we know that this was for a case of your tension and compression, right? So this was for a beam under bending. So I can go to the black fringe. It is just symmetrical about this. So this is essentially my color code I have, with which I can interpret that based on our earlier discussions. So let me keep that color code here. Let me keep that color code here, where this represents the sigma 1 minus sigma 2 equal to 0. Let me call sigma 1 minus sigma 2 equal to some constant k. So this is representing that k in some color, where this is 0 to some value. Actually, this will be 0, 1, 2, 3. We will see why that is in the later classes. But as of now, you just take it at word value, at face value. So here, in this case, A, we are able to see for the most part, where does it fall? For the most part, we are able to see this is the shade that is there. Nearly yellow to yellowish and white is what. So this plate with a hole is clearly stressed within this region only. Whereas here we are able to see those same shades come about, but we are also able to see certain patches of blue. So certain patches of blue also have come about. So how we can go about doing this is, I'll plot a box here. Let us say this is for A. Now what has happened for B? I'll change its color. What has happened for B is, for the most part, it is there, but certain shades of blue have also come. Certain shades of blue have also come about. Here, in addition to this, now I'm able to see the same. Now I'm able to see even more colors. So those certain shades of blue, then green, then yellow. So from here, I can see that it is almost stressed till here. All these colors are visible there, and it is given that it is for the same load. So what does that imply? That if I take this to be the metric, my plate with a hole is ideally it should have been uniform color throughout, but that didn't happen. So I had one case where the hole was circular and it was stressed till this region. Then the hole became elliptical. It got stressed a little more. Then once it degenerated into a crack, with the eccentricity going to zero or infinity, however you define it. Once that happened, the stress got raised much, much higher. So, with this in mind, let us try to answer the questions. Plate C is safer than plate A and B. Naturally, stress in C, if I say peak stress, let me represent it by sigma P. So, we know that sigma P in C is much greater than sigma P in B, which is greater than sigma P in A. This is something we just, with this discussion, we have deduced this. In such a case, plate C is safer than plate A and B is clearly not correct. Plate A is safer than plate B and C. A is safer than B and C because it is less stressed. So yes, this is true. Stress concentration factor for plate A is higher than that for B and C. So what is the stress concentration factor? Stress concentration factor is defined by sigma maximum, or as we have put here, sigma peak, which means sigma peak in this context, it is sigma p by sigma. That is whatever was intended at the far field. That is whatever was intended at the far field against what has developed near the discontinuities. Actually, what is the peak stress that has developed near the discontinuities? So in this case, this is the SCF. So we can clearly see if we were to rank this, given that sigma is same, so the denominator is same. So in terms of SCF also, SCF for C is much, much greater than for B, which is greater than SCF for A. So stress concentration factor for A is higher than that of plate B and C is not correct. It is clearly lower. Plate C is the dangerous among the three. Yes, because it has the maximum stress concentration factor. So the far field stress is essentially getting concentrated into a small region instead of spreading throughout the domain as it was intended to be. That is the one way to interpret that. So yes, it is most dangerous. So what does this tell us? That let us say that we design components assuming that they are defect free. But if there were to be some small defects, if there were to be some small defects, the stress for which we have designed gets multiplied by a large amount. It gets magnified by a large amount and it gets concentrated within one region. So what will essentially happen in that region? It will peak, the stress will peak and reach yield first. So as soon as this happens, there will be some portion that has yielded, but the stress is just continuing. So there will be some more portion that has yielded. So this will go on and on till the material has failed by the crack propagating and the separation of the material. So essentially, this is the essence behind this question. I hope I've done some justice to explaining that. And should there be any questions, you please feel free to ask. Okay. So let us look at this question. Which of the following statements are true regarding the principle of Moire? For small displacement measurements, grid on the specimen is viewed through another grid. Yes, as we saw in the last session also, that once we have a grid like that, and then we view it with some other grid. So there will be some interference patterns that will get developed based on the deformation that is happening. So that is the principle of Moire. For small displacements, grid on the specimen is viewed through another grid. True. Fineness of the grid spacing determines the accuracy of the measurement. Naturally, we cannot have uh, we have to have very fine grids in order to amplify the response. So if the grids are not very fine, then there is only so much displacement that we can measure, beyond which it will get masked into the grid patterns. So which is the essential difference between geometric moire and moire interferometry. In geometric moire, there is a certain threshold that in 1 mm you will have so many fine lines in the gratings. Whereas when we go to moire interferometry, it has reached even above 100 to 1000 lines in very sophisticated technologies, which make that grating. So it can measure whatever is the distance, it can measure at least that displacement. So essentially, its accuracy and precision increases as we increase the fineness. Strain can be obtained using the displacement measure using Moire, yes, provided it is Moire interferometry and not geometric Moire, because geometric Moire will give you displacements that are more inaccurate than that of Moire interferometry. And when we differentiate, take the gradient of the displacement, which is what is strain, those errors will magnify themselves. So when we measure displacements through Moire interferometry, your displacements are very precise. So the strain levels that you get by taking the gradient or from those measurements are reasonably accurate. Strain sensitivity can be improved with low density gratings. So as we saw, we have to go for high density gratings. Within the same distance, we have to pack much more more dense in number of that is within the same distance we have to pack more number of grids as compared to uh, less number of grids. So the density would have to be high in order for us to get high measurements, sensitive measurements. So strain sensitivity can be improved with high density gratings, not with low density gratings. So I hope that that is clear. Okay, so let us look at the next question. Photoelastic fringe patterns for a spanner tightening a nut is shown in the figure. There are 3 points in the spanner indicated by the letters A, B, and C. So we have a letter A here, B here, and C here. Identify the point where there is maximum stress concentration. Enter the letters in decreasing order of stress concentration. So essentially what we are saying is whichever is max, mid, and minimum is what we are trying to ask among these three. So again, let us bring in this color table and we'll try to reason it out. So I can just take this much because that represents one direction, 0 and above. So if I take this, now here, that parameter k, where sigma 1 minus sigma 2 is that k. We will see what that k is in the subsequent weeks. So here it is 0, 1, 2, 3. So from here we are able to see this is 0, this is black, and this is nearly this tint. So C is C is somewhere over here. C is clearly somewhere over here. This is C. And then if we go to B, B is somewhere over here. Somewhat yellow to this thing. And then if we go to A, it is near the blue region. And then that blue is followed by green. So here the blue is followed by yellow. Here the blue is followed by green. So A is essentially somewhere over here. A is somewhere over there in the scale. So with this, we can infer. Now we are doing this manually. When we do an experiment, and if we have a color table like this digitally generated from a known experiment, then what we can do, we can directly compare these values numerically, compare these numerical values, the intensity values, and we can interpret what is this parameter at that point, at every point in the domain. So this we will see as the application, the methods in photoelasticity that we use in order to measure, that we'll see in detail in the subsequent weeks. So this is by comparing the colors. So essentially we have A here, B here, and C somewhere over there. So sigma, or rather K for A is greater than K for B, greater than K for C. So A, B, C is our decreasing order in which we have to put them. So I hope that is clear. If there are any questions in what we are discussing, you please feel free to ask. In the meantime, I'll move on to the next question. Okay. Answer true or false. Similar kind of question. The thickness of a fringe is in most of the experimental techniques are uniform. Thickness of a fringe has nothing to do essentially with the experimental techniques. It has to do with the physics of the problem. As we saw in that same photoelasticity, we have fringes that appear like this, where we have its thickness is somewhat like that. With the same thickness, all the bands appear. All the bands appear nearly with the same thickness. In one case of a bent beam. For another case, as we deduced, if it was uniaxial tension, it will just be one fringe. So the thickness of the specimen itself is the thickness of that fringe. Whereas if we go here, we are able to see that this blue, this fringe is having this thickness, whereas here the thickness reduces. Similarly, I could give more examples based on this spanner also. Here we are able to see this blue has this thickness, whereas the same blue has a lesser thickness over here. So even no, not even within the domain, we are able to see variation in the thickness. So this is all stemming because of the mechanics or the physics of the problem, not from the experimental technique. So this is clearly false. The thickness of the fringe band is inversely related to the gradient of the variable it represents. So as we saw, so what would we anticipate in such a case? This is much thinner. Now as we go here, as we go towards this, we are able to see that the load would actually increase. So the fringe gradient also becomes higher. It can be clearly seen in this example. Actually, this is not shown fully, but what would happen is if we load it more, we'll be able to see that more and more fringes get concentrated here. And this is the point where the stress is at its peak. So as we go towards the stress concentration region, our fringes have a very high gradient. That is, from a particular value of K, it shoots to another very high value over a matter of a very small distance. So the gradient of that fringe is very, very high. In such cases, because each band, each color represents one particular fringe, so there will be a change in the colors that will happen at a very within a very small region. So what does that imply? That the fringe thicknesses will be very, very less in that area since it has to reach the peak. So the thickness of the fringe is inversely related to the gradient. If the gradient is high, that means variation in K is very high over the distance, or rather I should say, let this be that parameter. So delta K by delta X, if I talk about the X direction, so this has to be very, very high. In such a case, my thickness. So within this distance, I have to accommodate so many fringe orders, so many colors. So naturally, it will be inversely varying. So it is true. When fringes are closely packed, it is in the zone of low stress concentration. Now, when there is low stress concentration, we generally see that these fringes will be spaced out. For example, a case of uniaxial tension, we see that it is spaced out throughout the domain. It is uniform color. Whereas as soon as we put a hole, there is some concentration near that hole. And as that turns into an ellipse and into a crack, we are able to see that more and more fringes get closely packed near that stress concentration zone, where the stress concentration is high and not low. So this is clearly false. For a circular disk under diametral compression, the gradient of fringes is higher near the points of loading. So if we were to take this and apply a compression, for example, if we take a disk and subject it to a compression like that, what we will be able to see is we saw in the previous session that this is essentially a problem like that for an infinite section. This added with this added with a case of Lame's problem for radially outward tension. So the sum of these three is what makes up the solution for this disk under diametral compression. Now, if I were to take one of these cases, let us say that I take this case and then I blow it up, and then I see how actually fringes come about. That is how the contours look. They'll essentially be circular, and its shape can be, you can derive it based on theory of elasticity equations. So it will be like that. There'll be many more. I'm just drawing it. I'm just drawing some representative ones. So when we add this from here, if I were to take this and add it to this, So what I'll get, the final fringe pattern I'll get would be somewhat like that, and so on. So this is actually shown in the lecture. I'm just trying to explain it a little clearly. So what we see here is this band. This band has wide width. This will be wide. Now as we go, there'll be more and more. As we go towards the loading point, there are more and more fringes that are getting captured. So from here, if I were to draw a line, let us say that I draw a line like that. So I can see from here to this point, my gradient is very, very steep. So the thickness keeps on reducing. So that is what is asked in the question. That as we, for a circular disk under diametral compression, the gradient of the fringes are high near the loading point. So near the loading points, the gradient of the fringes becomes very, very high. So that is true. So I hope that that is clear. If there are any questions, you please feel free to ask. And what would be the pattern for the radial tension case? It will just be concentric circles essentially, because it's an axisymmetric problem. So it will be concentric circles. So when we add these three, we will essentially get some pattern like that, which is shown beautifully in the lecture. I'm just trying to draw it roughly in order to explain. So I hope that is clear. So, okay. So anyway, I have run out of questions now. So if there is anything that I can answer, that any questions that you have that I can answer, I'll be happy to take them now. Because anyway, I've solved the assignment and I've run out of questions. So you please feel free to ask should there be anything. Are there any questions, Mr. Shiva Kumar? Clear? Okay, okay. Well, if there are no questions, because I have nothing more to solve here. So if anything you want me to explain better, I can do that. If there are no further questions, then it is better we can close. That is also not a. Okay, thank you. Thank you.